Hello everyone, welcome to this session. In today's video, we are going to clearly understand one of the most important concepts for every .NET developer, the SOLID principles. If you really want to move from beginner level coding to professional enterprise level development, if you want to write code that is clean, maintainable, scalable, and easy to extend, and if you want to succeed in real-time projects, interviews, and your software career, then SOLID is something you must master. In this session, you will learn what SOLID is, why SOLID matters, how it is used in .NET real-time development, and we will discuss each principle one by one with simple explanations and practical thought process examples. So stay with me till the end. This session is going to be extremely valuable. Before we dive into each principle, let us first understand what SOLID actually means. SOLID is a collection of 5 important design principles introduced by Robert C. Martin, also known as Uncle Bob. These principles help developers design better software systems. SOLID mainly focuses on object-oriented design, meaning how we design classes, how we design relationships between classes, and how we structure our application. So SOLID stands for S. Single Responsibility Principle, O. Open-Closed Principle, L. Liskov Substitution Principle, I. Interface Segregation Principle, D. Dependency Inversion Principle. When we follow SOLID, our code becomes easier to test, easier to maintain, easier to change, and easier to extend in the future. So now, let us clearly understand each principle one by one. Single Responsibility Principle. Let us start with the first principle, Single Responsibility Principle. This simply says, a class should have only one reason to change. In simple words, one class should do only one job. Imagine you have a class which is handling business logic, database logic, and also sending emails, everything inside a single class. This class will become very large. And whenever database changes, you need to modify it. Whenever email changes, again you modify it. Whenever business logic changes, again you modify it. This makes your application hard to maintain and very risky. Instead, we should separate responsibilities. One class should handle business rules, another class should handle database saving, another class should handle email notification. Now every class has only one job. This is exactly what Single Responsibility Principle is. In real time, this principle is used everywhere in .NET. In e-commerce order processing, logging systems, payment processing, notification systems. Following SRP makes your code neat, clean, readable, testable, and professional. Now let us move to the second principle, Open-Closed Principle. This principle says, software entities should be open for extension but closed for modification. What does that mean in simple language? It means, you should be able to add new features without changing the existing working code. For example, imagine you are building a payment system. Initially you support credit card payment. Later you want to add UPI payment. Then you want to add net banking. Then PayPal. Then wallet. If you keep modifying the same class again and again, one day it will break. Also, modifying tested working code is always risky. Instead, Open-Closed Principle says, don't modify existing class, just extend the system by adding new classes. In .NET we achieve this using abstraction, inheritance, interfaces, polymorphism. This is extremely useful in real-time applications such as payment gateways, discount calculators, tax calculations, notification systems. So the takeaway is, do not keep modifying your old code, design your system so that you can easily extend it. Now let's discuss the third principle, Liskov Substitution Principle. This principle says, a derived class must be completely substitutable for its base class. In simple words, if class B inherits from class A, then wherever A is expected, B should work without breaking the system. For example, if you create a base class called bird and add a fly method, and then you create an ostrich class inheriting from bird, but ostrich cannot fly. So if someone calls fly on ostrich, your application crashes. This violates Liskov substitution. So instead, design your classes meaningfully, separate birds that fly and birds that don't fly. Never force a subclass to behave against nature. This principle ensures correct inheritance, logical object hierarchy, stable design, no unexpected runtime behavior. This is widely applied in vehicle systems, shape hierarchies, employee management systems, banking systems. So always remember, Child class should never break the expectations of parent class. Now let us look at the fourth principle, interface segregation principle. This principle says, do not force a class to depend on methods it does not use. In simpler words, do not create one large interface with so many unnecessary methods. Create small, meaningful, and focused interfaces. For example, if you create an interface that has work and eat methods, and then you force a robot class to implement it, robot does not eat. So you are forcing the robot class to implement something it doesn't need. This is bad design. Instead, break the interface into work interface, eat interface. Now only those who need eat will implement eat, those who only work will only implement work. This principle improves flexibility, clarity, reusability, maintainability, and it is heavily used in clean architecture, microservices, solid API designs, enterprise applications. So always create small, meaningful interfaces instead of one giant interface. Now let's talk about the fifth and final principle, dependency inversion principle. This is one of the most important concepts in modern .NET development. This principle says, high-level modules should not depend on low-level modules. Both should depend on abstractions. In simple words, your main business logic should not directly depend on concrete classes. It should depend on interfaces or abstractions. For example, if your notification service is tightly connected to email service, then tomorrow if you want SMS, WhatsApp, or push notification, you must modify the notification service. But if your notification service depends on an interface, then you can easily plug any notification type without changing main logic. This principle is the reason why dependency injection exists in ASP.NET Core. In fact, modern .NET frameworks are completely built around this principle. Benefits include flexible design, easy switching between implementations, better testing, loose coupling, professional architecture. So always depend on abstractions, not concrete classes. Now you may ask, where exactly are solid principles used in real projects? They are used everywhere. Checkmark ASP.NET Core Clean Architecture, checkmark Domain-Driven Design, checkmark Microservices Architecture, checkmark Onion Architecture, checkmark Enterprise ERP Systems, checkmark Banking Applications, checkmark E-commerce Systems. Whenever companies design large systems, maintainable systems, and long-term scalable products, Solid plays a very important role. Solid helps your code remain clean, testable, flexible, professional, and companies give very high importance to these concepts during interviews also. Final summary and closing. So finally, let us summarize everything we learned. S. Single responsibility principle. One class should have only one reason to change. Keep one class for one job. O. Open closed principle. Open for extension, closed for modification. Add new features without touching old code. L. Liskov substitution principle. Subclasses should behave like their base classes. Never break expectations. I. Interface segregation principle. Create small and meaningful interfaces. Do not force classes to use unwanted methods. D. Dependency inversion principle. Depend on abstractions, not on concrete implementations. Use dependency injection. If you follow Solid, your code becomes professional. It becomes easy to maintain. It becomes future-proof. And you will stand out as a strong .NET developer. Thank you so much for watching this session. If you learned something valuable today, make sure to like the video, comment your thoughts, share this with your developer friends, and subscribe for more real-time .NET development content. See you in the next session. Happy coding! Welcome to Vidyaskatra YouTube channel, a dedicated place for developers, learners, and professionals to upgrade their knowledge with real-world concepts and practical explanations. Hey developers, welcome back to the channel. In today's session, we are going to unlock one of the most important concepts in clean coding and professional software development, the single responsibility principle. If you have ever faced messy code, bugs after every update, confusion while maintaining projects, or fear of touching old code, then this video is absolutely for you. I will explain SRP in super simple language with real examples, real coding scenarios, powerful explanations, and complete clarity. Watch this video till the end, because once you understand SRP properly, your coding style will never be the same again. Let's begin. So now, let's understand what exactly the single responsibility principle is. The single responsibility principle, also called SRP, simply means that a class, module, function, or component should have only one reason to change. In other words, anything we create in software should focus on only one responsibility, just one job, and nothing more. Think of it like this. If a class is taking care of multiple unrelated tasks, handling too many things at once, and trying to behave like a superhero class, then it is definitely breaking the single responsibility principle. So remember this in the simplest way. A class should do only one job, a class should focus on one responsibility, and a class should never mix multiple unrelated tasks inside it. If it does, then sooner or later, the code becomes messy, confusing, and very difficult to maintain. That is why SRP is so important. It keeps your code clean, clear, and professional. Now let's understand the single responsibility principle in very simple and practical language. Imagine a person working in a company. But instead of having one clear role, this single employee is doing everything. He is working as a software developer, a tester, an HR manager, an accountant, and also a marketing executive. What do you think will happen? Naturally, this person will get confused. Their work will become completely messy. If the HR policy changes, their work changes. If tax rules change, their work changes. If marketing strategy changes, again they have to change the way they work. This makes their role unstable, stressful, and extremely difficult to manage. The same thing happens in programming. When one class handles too many responsibilities at once, that class becomes tightly coupled, difficult to maintain, difficult to modify, risky to change, and highly prone to bugs. So the single responsibility principle gives us a very powerful and clear message. One class equals one purpose, one module equals one responsibility, one function equals one clear task. When every part of the software has only one responsibility, the system becomes cleaner, easier to understand, easier to maintain, and far more professional. So now the question is, why is the single responsibility principle so important? Why do developers, architects, and big companies constantly talk about SRP? Let's understand the real power behind it. Makes code easy to understand. When a class has only one responsibility, it becomes extremely easy to read and understand. Any developer can open that file and immediately know what it does. Instead of scrolling through hundreds of lines of confusing and mixed up logic, they can instantly identify the exact purpose of that class. Simple responsibility means simple understanding, and simple understanding means better development. Makes code easy to maintain. Software is never permanent. New features come, business rules change, performance needs improvement, and customers demand updates. If your class is handling only one job, making changes becomes very safe, easy, and fast. You don't have to worry about breaking other functionalities because you are modifying only the part related to that specific responsibility, reduces bugs and errors. When multiple responsibilities are tightly packed inside one class, changing one part can accidentally break another. That's where most hidden bugs come from. But when we follow SRP, responsibilities are well separated. So if something goes wrong, we immediately know where to look, and fixing issues becomes much simpler and safer. Encourages reusability. When each class is focused on a single responsibility, those classes become highly reusable. Other modules, other teams, or even completely different applications can use them easily without modification. Clean separation naturally leads to reusable and professional code, improves testability. Unit testing becomes incredibly simple with SRP. Since each class is responsible for only one thing, we can test that one responsibility independently. Tests become clearer, faster, and far more reliable. This is one of the biggest reasons why SRP is loved in real-world enterprise projects. Why is the single responsibility principle so important? Why do developers, architects, and big companies constantly talk about SRP? Let's understand the real power behind it. Makes code easy to understand. When a class has only one responsibility, it becomes extremely easy to read and understand. Any developer can open that file and immediately know what it does. Instead of scrolling through hundreds of lines of confusing and mixed up logic, they can instantly identify the exact purpose of that class. Simple responsibility means simple understanding, and simple understanding means better development. Makes code easy to maintain. Software is never permanent. New features come, business rules change, performance needs improvement, and customers demand updates. If your class is handling only one job, making changes becomes very safe, easy, and fast. You don't have to worry about breaking other functionalities because you are modifying only the part related to that specific responsibility, reduces bugs and errors. When multiple responsibilities are tightly packed inside one class, changing one part can accidentally break another. That's where most hidden bugs come from. But when we follow SRP, responsibilities are well separated. So if something goes wrong, we immediately know where to look, and fixing issues becomes much simpler and safer. Encourages reusability. When each class is focused on a single responsibility, those classes become highly reusable. Other modules, other teams, or even completely different applications can use them easily without modification. Clean separation naturally leads to reusable and professional code, improves testability. Unit testing becomes incredibly simple with SRP. Since each class is responsible for only one thing, we can test that one responsibility independently. Tests become clearer, faster, and far more reliable. This is one of the biggest reasons why SRP is loved in real-world enterprise projects. So overall, the single responsibility principle makes your code clear, maintainable, stable, reusable, and highly professional. That's why SRP is not just a theory. It is a real-life foundation of clean and long-lasting software. Now the next important question is, where should we actually apply the single responsibility principle? Is it only for classes? Or is it something much bigger? Well, SRP is not limited to just classes. We should apply it to almost every level of software development. We apply SRP to classes, methods, services, microservices, API layers, UI components, modules, folders, and even entire projects. Wherever there is functionality, simply ask yourself two simple questions. Is this doing only one job, or is it handling multiple responsibilities? If you realize that something is doing too many things at once, then it's time to split it. Give every part of your system one clear purpose and one clear responsibility. When you do that, your software becomes cleaner, more modular, easier to understand, and far more professional. So one class is now directly connected to multiple areas of the system, and that is extremely dangerous, because it makes the class hard to maintain, hard to extend, hard to test, risky to modify, and definitely not reusable. This is exactly why the single responsibility principle says, do not dump everything into one class. Give every responsibility its own dedicated place. Now let's see how we can fix this problem using the single responsibility principle and convert our bad design into a clean, professional, and maintainable design. Instead of keeping everything inside one class, we simply separate the responsibilities into different classes. Each class will now focus on only one job, one responsibility, and one clear purpose. Create a validation class. First, we create a dedicated class only for user validation. Public class user validator. Public void validate, user. If string is null or empty, user. Email. Throw new exception, email is required. This class has just one responsibility, to validate the user. Create a repository class for database. Next, we create another class only for database saving. Public class user repository. Public void save, user. Console. Write line, user saved. This class is responsible only for storing the user. Create an email service class. Now we separate the email sending logic. Public class email service. Public void send welcome email, user. Console. Write line, welcome email sent. This class has a single purpose, sending welcome emails. Create a logger class, then we separate logging functionality. Public class logger, public void log, string message, console, write line, message. This class has one clear job, logging. Finally, a clean and simple user service class. Now our main service becomes clean, readable, and focused. Public class user service. Private read-only user validator underscore validator equals new user validator. Private read-only user repository underscore repository equals new user repository. Private read-only email service underscore email service equals new email service. Private read-only logger underscore logger equals new logger. Public void register user underscore validator. Validate user underscore repository. Save user underscore email service. Send welcome email, user underscore logger. Log, user registered successfully. Now this class is not doing everything by itself. It is simply coordinating the work between other classes. Each responsibility has its own dedicated home. By applying SRP, our code becomes cleaner, easier to maintain, easier to test, reusable, and highly professional. This is how we convert a tightly coupled, messy design into a clean and structured architecture using the single responsibility principle. Now, after applying the single responsibility principle, our design becomes clean, structured, and perfectly organized. The system now has one class responsible only for validation, one class responsible only for data persistence, one class responsible only for sending emails, one class responsible only for logging, and one main class simply coordinating the work. Now each class has just one clear reason to change. Each class is easy to understand, easy to maintain, easy to reuse, and very easy to test. Most importantly, the system becomes scalable. If we want to change validation, we only modify the validation class. If we change the database, only the repository class changes. If email service changes, only the email class is affected. So instead of one big risky class, we now have small, focused, and powerful components. Exactly how professional software should be designed. Now let's talk about the biggest question. What are the advantages of following the single responsibility principle? Why do so many companies, architects, and experienced developers strongly recommend SRP? Let's break it down. Better readability. When each class has only one responsibility, the code becomes crystal clear. Every class clearly explains what it does, and even new developers can quickly understand the system without confusion. Easier maintenance. Software constantly changes. Features get added, rules get updated, and improvements are required. With SRP, updating code becomes very safe and easy because you only modify the class responsible for that particular functionality. No unnecessary risk to the rest of the system. Improved reusability. Single responsibility classes are highly reusable. Since they are focused and independent, the same modules can be used in other parts of the project, or even in other projects, without major changes. Better testability. Testing becomes simple and powerful with SRP. Each class does only one predictable job, so unit tests are easier to write, easier to understand, and much more reliable. Reduces bugs. Less code inside each class means fewer bugs. And even if a bug appears, it becomes very easy to locate and fix because responsibilities are clearly separated. Supports clean architecture. SRP is not just a small coding guideline. It is a foundation of professional software design. It strongly supports SOLID Principles, Microservices architecture, clean architecture, onion architecture, and domain-driven design. When SRP is followed, every other architecture practice becomes easier and more effective. So overall, the single responsibility principle makes your software cleaner, safer, easier to maintain, more professional, and future-ready. More classes. When we split responsibilities, the number of classes in the project naturally increases. For beginners, this sometimes feels overwhelming or too much, but in reality, this is actually a positive thing for professional development because more classes mean more clarity, better structure, and cleaner architecture. Slightly more design effort. Applying SRP requires thinking before coding. You need to plan your design, understand responsibilities, and structure things properly. Beginners often feel this is time-consuming, but in long-term projects, SRP actually saves massive time by reducing bugs, avoiding confusion, and simplifying maintenance. Risk of over-engineering. Sometimes developers go to the extreme. They split even very small logic into too many classes, which only increases complexity instead of solving problems. So SRP must be applied smartly and logically, not blindly. Perfectly aligned with your previous toned-down finger. SRP in microservices. In microservices architecture, SRP is extremely powerful. Each microservice should handle one bounded business responsibility. For example, a payment service handles only payments, an order service manages only orders, an inventory service manages product stock. Each service focuses on one domain, which makes systems scalable, independent, and robust. SRP in APIS. Even in APIS, SRP plays a key role. We should always separate. Controller logic handles requests and responses, business logic handles real operations, data access logic interacts with the database. This separation keeps APIS organized, readable, and easy to maintain. SRP in UI. SRP is also important in UI development. We should separate UI components only for display, state management, handles data flow, business logic handles decisions and rules. When UI responsibilities are separated, applications become more stable and easier to manage. Now, how do we identify if SRP is violated? Just ask yourself these simple questions. Does this class do more than one job? Does this class frequently require changes? Does changing one functionality risk breaking others? Is this class hard to understand? Does this class cross multiple business domains? If the answer is yes, then SRP is clearly violated. SRP in interview perspective. If you are attending an interview, here's how you can confidently answer SRP questions. What is SRP? A class should have only one responsibility, meaning only one reason to change. Why is SRP important? Because it improves maintainability, readability, scalability, and testability. Give a real example: user registration system where validation, email sending, logging, and database storage are separated into different classes. What happens if SRP is not followed? Code becomes messy, tightly coupled, error-prone, and extremely difficult to maintain. Final practical takeaways. So practically remember, do not mix unrelated logic in one class. Each class should represent one clear purpose. Always think about future changes. Apply SRP logically, not blindly. SRP is your friend, not a rule to fear. Conclusion: the single responsibility principle is one of the most powerful concepts any developer can learn. It transforms messy, fragile, spaghetti code into structured, professional, enterprise-grade software. When we design applications where every class, every module, and every service has one focused responsibility, the system becomes clearer, stronger, scalable, and future-proof. Yes, SRP may feel like extra effort in the beginning, but in real-world software development, where applications live for years and continuously evolve, the single responsibility principle saves massive time, prevents countless bugs, and makes development far easier. So always remember, one class, one responsibility, one reason to change. That is the true essence of the single responsibility principle. If you found this explanation helpful, don't forget to like the video, share it with your developer friends, and subscribe to the Videoscatra YouTube channel for more high-quality learning content. Also, hit the bell icon so you never miss an update. Welcome to Videoscatra YouTube channel, a dedicated place for developers, learners, and professionals to upgrade their knowledge with real-world concepts and practical explanations. Hey developers! Welcome back to the channel. In today's session, we are going to unlock one of the most important principles in clean coding and professional software development, the open-closed principle. If you've ever faced messy code, bugs appearing after every update, confusion while maintaining projects, or fear of touching old code because something might break, then this video is absolutely for you. Today, I'm going to explain the open-closed principle in the simplest way possible with real examples, real coding scenarios, and crystal clear explanations. Now let's understand the official definition of the open-closed principle. The open-closed principle states that software entities like classes, modules, and functions should be open for extension but closed for modification. It means our existing, working code should remain untouched and safe, but we should still be able to add new features or behaviors whenever needed. Instead of changing old code and risking new bugs, we extend the system using concepts like interfaces, inheritance, and design patterns. By following OCP, we make our applications more stable, easier to maintain, and future-ready, even when business requirements keep changing. So now the big question. Why do we need the open-closed principle? Why is it so important in real-world software development? Because in real projects, requirements are never permanent. Clients change their minds, new features are added, business rules evolve, and applications keep growing. If every time a new requirement comes, we start modifying old code, we increase the chances of breaking existing features, introducing new bugs, and making the system unstable. By following the open-closed principle, our code becomes safer and more reliable, because the tested and working logic remains untouched. We simply extend the system by adding new modules or classes instead of modifying old ones. This makes the software easier to maintain, easier to upgrade, and much more scalable. In simple words, OCP helps us build professional, flexible, and future-proof applications that can handle change without fear of breaking things. So now let's talk about where we actually use the open-closed principle in real life. We apply the open-closed principle in any place where our software is expected to grow, change, or receive new features in the future. This includes areas like payment systems, notification systems, logging, reporting, business rules, and almost any feature that may need frequent updates. Instead of modifying old code again and again, we design our system in a way that allows us to simply plug in new functionality. You'll see OCP used in large enterprise applications, banking systems, e-commerce platforms, and cloud-based solutions where stability is extremely important. Whenever we know that this feature may expand later, that's the perfect place to apply the open-closed principle. In short, we use OCP wherever we want flexibility, scalability, and safe growth in our software. Now let's understand how we actually implement the open-closed principle in real development. We follow OCP by designing our system in such a way that new features can be added without modifying existing code. And we achieve this mainly using abstraction and polymorphism. Instead of writing logic directly inside one big class, we create interfaces or abstract classes and define common behavior. Then, whenever a new requirement comes, we create a new class that implements or extends that abstraction. This way, we only add new code, we don't change the existing working code. We can also use popular design patterns like strategy pattern, factory pattern, dependency injection, and plugin architecture to follow OCP more effectively. These patterns allow us to plug in new behavior easily, just like adding a new module to a system. So in simple words, we apply the open-closed principle by designing flexible code using abstraction, writing extensible modules, and adding new features through extension instead of modification. Let's now look at some real-world practical examples where the open-closed principle is actually used in the software we use every day. Example 1: Payment systems. Think about e-commerce websites like Amazon, Flipkart, or any online shopping platform. Initially, they may support only credit card payments. Later, they need to add UPI, net banking, PayPal, wallets, and many more options. Do they rewrite the entire payment code every time? Of course not. They design the payment module using abstraction so new payment types can be added as separate classes without modifying the existing working code. This is the open-closed principle in action. On the left side of this image, we see a clear violation of the open-closed principle. Here, we have a single large payment processor class, often called the God processor, because it tries to handle everything inside one place. Inside this class, we keep writing multiple if and else if conditions like credit card, UPI, net banking, and PayPal payments. Every time a new payment method is required, we open this class again, modify the code, add more conditions, and risk breaking existing working functionality. This approach is risky to change, prone to bugs, hard to test, difficult to maintain, so this clearly breaks the open-closed principle, because we keep modifying the same existing working class again and again. Now look at the right side. This shows OCP done correctly. Here, we design the system using abstraction. We create an iPayment interface that defines a stable contract with a pay amount method. Our payment processor now becomes closed for modification and depends only on this interface. Now whenever we need a new payment type, we simply create a new class such as credit card payment, UPI payment, or PayPal payment, each implementing the iPayment interface. We extend the system by adding new classes instead of modifying old working code. This approach is safe to extend, stable and maintainable, easy to test, future-proof, and that's the core idea of the open-closed principle. Add new functionality by adding new classes, not by constantly changing the existing payment processor. Example 2: Notification systems. Consider applications that send notifications. At first, they may support only email notifications. Later, requirements come to add SMS, then push notifications, then WhatsApp alerts. Again, instead of changing the old notification logic, developers add new notification classes that extend the same interface. Old code remains safe, new features get added smoothly. On the left side of this image, we see a clear violation of the open-closed principle. Here, we have a single large notification service class, often called the God class, because it handles everything. Inside this class, we keep writing multiple if and else if conditions like email, SMS, push, and WhatsApp notifications. Every time a new notification type is required, we open this class again, modify the code, add new conditions, and risk breaking the existing working features. This approach is risky to change, prone to bugs, hard to test, difficult to maintain, so this clearly breaks OCP, because we keep modifying existing working code. Now look at the right side, this is OCP done correctly. Here, we design the system using abstraction. We create an interface called iNotification which defines a stable contract, like a send message method. Our notification service becomes closed for modification and depends only on this interface. Now whenever we need a new notification type, we simply create a new class like email notification, SMS notification, push notification, or WhatsApp notification, each implementing the same interface. We extend the system by adding new classes instead of modifying the old one. This approach is safe to extend, stable and maintainable, easy to test, future-proof, and that's the core idea of the open-closed principle. Add new functionality by adding new classes, not by constantly changing the existing working code. Plugin architecture. Applications like VS Code, browser, and game engines allow plugins. You can install themes, extensions, tools, all without changing the original software. The base system is closed for modification but open for extension through plugins. This is a perfect real-world demonstration of OCP. This image demonstrates one of the best real-world implementations of the open-closed principle, known as plugin architecture. In the center, we have the base system. This is the main application and it is clearly marked as closed for modification, meaning once the core system is built, we don't keep editing or changing it every time new requirements come. Instead, the system provides slots or extension points, like theme slot, extension slot, tool slot. Now look at the left and right sides. Here we have plugins, such as theme plugin, tool plugin, extension plugin. These plugins are open for extension, which means developers can keep building and adding new plugins anytime without touching the original base system. Whenever we want to add a new theme, new feature, or new tool, we don't modify the base application. We simply plug in a new module into the respective slot. The base system stays safe, stable, and unchanged, while new functionality keeps getting added smoothly. This is exactly how applications like VS Code, browser, IDEs, and many enterprise systems work. They follow the open-closed principle by keeping the core system closed, but making the plugin ecosystem open for endless extensions. And that's the key takeaway of this image. New functionality is added via plugins, the original software remains unchanged. This makes the system flexible, scalable, and future-proof. Example 3. Tax calculations and business rules. In banking, finance, or government systems, tax rules and business policies frequently change. If developers modify the same code repeatedly, it becomes a bug factory. So they follow OCP. Existing logic stays untouched and new rules are added as new modules. This keeps the system stable even when laws and policies keep changing. In this example, we are looking at how the open-closed principle works in a real-world tax calculation system. On the left side of the image, we see the wrong approach, a tax calculator designed as a single, God module. Inside this one big class, all tax rules are written using multiple if and else if conditions like old rule 1, old rule 2, and even the latest new tax rule 2024. Every time the government updates tax policy, developers must reopen this same calculator, change its logic, and add more conditions. This is extremely risky, because modifying existing working code can easily introduce new bugs. It also makes the system hard to maintain, hard to test, and highly unstable as it grows. This completely violates the open-closed principle because we keep modifying instead of safely extending the system. Now look at the right side. This is the correct professional way to design it. Instead of writing all rules inside one class, we create a stable interface called iTaxRule with a method like calculate income. The tax calculator now depends only on this interface and becomes closed for modification. Whenever a new tax rule comes, we do not change the tax calculator. Instead, we simply create a new class like GST. In applications, logging may initially be done to a file. Later, you may need to log to a database, cloud, or monitoring tool. Instead of rewriting the logging system, we just add new logger classes. Again, no modification, only extension. So in simple words, whenever a system is designed to grow safely without rewriting old code, the open-closed principle is working behind the scenes. This image clearly demonstrates how the open-closed principle can be applied in a logging system. In the center, we have the main logging system, which is marked as base code, closed for modification. That means once the logging framework is developed, we don't keep changing its internal code every time we need a new logging feature. Instead, the system relies on a logger interface that defines a simple, stable contract with a method like log message. This interface never changes and acts as the foundation of the entire logging mechanism. Now look at the loggers around it. We can have a file logger, a database logger, and a cloud logger, and each one simply extends the logger interface and implements its own logging mechanism. If tomorrow the project requires a new type of logger, like an email logger or monitoring logger, we don't modify the original logging system. We simply create a new class that implements the same interface. This way, we are adding new functionality through extension, not modification, which perfectly follows the open-closed principle. This design keeps the core system stable, reduces bugs, makes the code cleaner, and makes testing much easier because each logger can be tested independently. Most importantly, it makes the system highly scalable and future-ready because new loggers can be plugged in anytime without touching the existing secure and tested code. The key takeaway is simple. New loggers are added via extension while the base logging system remains unchanged. That is the real power of the open-closed principle. Now let's talk about the advantages of the open-closed principle and why it is so powerful in real-world software development. First, it makes our code stable and reliable. When we don't modify existing working code, we don't accidentally introduce new bugs. The tested code remains safe, and the application becomes much more trustworthy. Second, it gives us easy scalability and future growth. As new requirements come, we simply add new classes or modules instead of rewriting old ones. This makes it super easy to enhance the system without fear. Third, it improves maintainability. Code that follows OCP is clean, modular, and well organized. Developers can easily understand it, update it, and extend it even after years, which is extremely important in enterprise projects. Fourth, it supports team collaboration. Different developers can work on new features independently by creating new extensions without touching each other's code. This reduces conflicts and improves productivity. Fifth, it encourages good design practices. By using abstraction, interfaces, and design patterns, OCP helps developers think in a professional and architectural way rather than just writing quick fixes. In simple words, the open-closed principle helps us build robust, scalable, maintainable, and future-ready software that can grow smoothly as requirements change. Now let's talk honestly. Even though the open-closed principle is powerful, it also has some disadvantages and limitations that every developer should know. First, it can increase code complexity. To follow OCP, we often use abstractions, interfaces, and multiple classes. This can make the design heavier and more complex than necessary, especially for small projects or simple requirements. Second, it may lead to too many classes and files. Every new feature is added as a new class instead of modifying an existing one. Over time, this can create a large number of classes, making the project harder to navigate if not structured properly. Third, OCP requires good design thinking and experience. Beginners may overuse it or apply it in the wrong places. If implemented without proper understanding, it can actually make the system confusing instead of improving it. Fourth, it can sometimes result in indirect changes instead of real simplicity. Even though we don't modify old code, we may need to update factory logic, configurations, or dependency injections, which still requires careful handling. Finally, it may be overkill for small or rarely changing features. If a feature is not expected to change frequently, designing it with heavy abstractions might just waste time and effort. So while the open-closed principle is extremely useful, it should be applied wisely and only where necessary, with proper planning and understanding. Now let's understand how the open-closed principle works in microservice architecture and why it is extremely powerful in modern cloud-based systems. In microservices, every feature is developed as an independent service, like payment service, order service, notification service, user service, and so on. Here, the open-closed principle fits perfectly because each microservice should be open for extension and closed for modification. Instead of changing an existing service again and again, we extend the system by adding new services or new versions of services. For example, if your application currently has a credit card payment service and tomorrow you want to add UPI or PayPal, you don't modify the existing service heavily. You simply create a new microservice or a new implementation and plug it into the architecture. The existing working service remains safe, stable, and untouched. This is OCP in action. Similarly, in notification microservices, you might start with email notifications. Later, when you need SMS, push notifications, or WhatsApp alerts, you simply add new services without breaking the old one. Microservices naturally support OCP because they are loosely coupled, independently deployable, and designed to grow by extension rather than modification. This approach gives us better scalability, zero or minimal risk to existing features, faster development, ability to add new capabilities without breaking production. However, we must also be careful. Too many microservices without proper design can increase complexity. So, OCP should be applied wisely with proper architecture planning, API design, and version control. In simple words, microservices plus open-closed principle equals highly flexible, scalable, and future-proof software systems. So that brings us to the end of this powerful session on the open-closed principle. We learned what OCP is, why it is important, where it is used, how to apply it, real-world examples, advantages, disadvantages, and even how it fits perfectly in microservice architecture. If you truly understand this principle and start applying it in your projects, your code will become cleaner, safer, more scalable, and truly professional. Remember, great developers don't just write code, they design systems that handle change confidently. If you found this video helpful, make sure to like the video, subscribe to the channel, and share it with your developer friends. Drop your thoughts, doubts, or topics you want next in the comments. I'd love to help you learn more. Thank you so much for watching. This is Vidyaskatra channel, helping you become a smarter and stronger developer. See you in the next video. Until then, keep learning and keep coding. Rocket. Welcome to Vidyaskatra YouTube channel, a dedicated place for developers, learners, and professionals to upgrade their knowledge with real-world concepts and practical explanations. Hey developers! Welcome back to the channel. In today's session, we are going to unlock one of the most important principles in clean coding and professional software development, the Liskov substitution principle. If you've ever faced messy code, unexpected bugs after updates, confusion while maintaining projects, or fear of modifying existing classes because something might break, then this video is absolutely for you. Today, I'm going to explain the Liskov substitution principle in the simplest way possible with real examples, real coding scenarios, and crystal clear explanations so you can confidently apply it in your projects. Watch till the end. Once you understand LSP properly, your object-oriented design mindset will completely transform. Let's begin. Now let's understand the official definition of the Liskov substitution principle. The Liskov substitution principle states that objects of a superclass should be replaceable with objects of its subclass without breaking the functionality of the system. In simple words, if class B is a child of class A, then we should be able to use B anywhere A is expected, and the application should still work correctly without unexpected behavior, errors, or logical changes. Subclasses should honor the behavior, rules, and expectations defined by the parent class. They should extend functionality, not change it in an unexpected way. By following LSP, we ensure our inheritance structure is meaningful, logical, and reliable. It prevents us from creating subclasses that, technically, inherit but behave completely differently and cause hidden bugs. Because in real-world software development, inheritance is widely used, and if subclasses break the behavior of base classes, systems become unstable. Requirements change, features evolve, code grows over time, and if subclasses don't maintain consistent behavior, the entire system becomes risky to modify and maintain. Violating LSP leads to unexpected outputs, broken logic, runtime issues, and fragile designs. By following LSP, our code becomes more predictable, more stable, easier to maintain, safer to extend. Developers can confidently substitute subclasses without fear of breaking existing functionality. This leads to clean loop design, better architecture, and truly professional-grade software. In simple words, the Liskov substitution principle helps us build professional, reliable, and predictable applications, where subclasses truly behave like their parent classes without breaking functionality or introducing unexpected behavior. It ensures that inheritance is meaningful, logical, and trustworthy in real-world projects. So now let's talk about where we actually use the Liskov substitution principle in real life. We apply LSP anywhere we use inheritance or polymorphism. This includes areas like payment processes, notification systems, user roles, geometry systems, tax systems, validation frameworks, and business rule engines. Whenever a subclass is created to replace or extend a base class, LSP ensures it behaves correctly without changing the expected outcome of the system. In simple words, wherever child classes stand in place of parent classes, LSP must be followed. You'll see LSP heavily used in large enterprise applications, banking systems, e-commerce solutions, frameworks, and libraries where stability and predictable behavior are extremely important. Whenever we know that different implementations will be substituted at runtime, that's the perfect place to apply the Liskov substitution principle. In short, we use LSP wherever we want consistency, correctness, and safe inheritance in our software. We apply LSP by ensuring that every subclass can truly act as a substitute for its parent class without breaking functionality. That means child classes should not remove expected behavior, should not throw unexpected exceptions, should not change input-output meaning, and should not violate the rules promised by the base class. Instead of blindly inheriting and overriding methods in a risky way, we design carefully. Subclasses must follow the same contract, respect business rules, and behave logically like the parent. If a subclass cannot naturally behave like a parent, then inheritance should not be used. Composition or separate abstraction is a better choice. We also use principles like behavioral consistency, meaningful overriding, respecting method expectations, avoiding surprise behavior. In many systems, we implement LSP together with interfaces, abstraction, and clean inheritance structures to ensure the design remains stable, predictable, and easy to maintain. So in simple words, we apply Liskov substitution principle by designing subclasses that truly behave like their parent classes, ensuring no surprises, no broken logic, and no unexpected behavior, only safe substitution and reliable functionality. Let's now look at some real-world practical examples where the Liskov substitution principle is actually used in the software we use every day. Example, payment systems. Think about e-commerce platforms like Amazon, Flipkart, or any online shopping website. They may support different payment types such as credit card, UPI, net banking, and PayPal. All these payment types usually inherit from a common payment base class or implement a common interface. Now here comes the main idea of Liskov substitution principle. Anywhere the system expects a base payment type, we should be able to substitute it with any payment subclass like credit card payment, UPI payment, or PayPal payment. And everything should still work correctly without breaking the system or changing its behavior unexpectedly. LSP violation. On the left side, imagine a bad design where subclasses do not behave like the parent class. For example, suppose the base class defines a pay amount method, but one of the subclasses changes the meaning of the method, restricts functionality, throws unexpected exceptions, or behaves differently than what the system expects. This creates huge problems. The system becomes unpredictable, replacing parent with child breaks the application, bugs appear when different payment types are used, the design becomes unreliable and hard to maintain. This clearly violates the Liskov substitution principle because subclasses cannot safely replace the base class. LSP done correctly, right approach. Now look at the correct design. We first define a payment base class or payment interface that defines a clear and consistent contract like pay amount. Every payment type such as credit card payment, UPI payment, and PayPal payment follows the same behavior, same expectations, and same rules. They do not break functionality, they do not change the meaning of the operation, and they do not surprise the system. So now, we can safely substitute any payment subclass. The system works smoothly without modification, behavior remains consistent and predictable, the design becomes stable, professional, and reliable. Core meaning of LSP here: if the system expects a payment type, we should be able to pass any valid payment subclass, and the system should still work correctly, without failing, without breaking, and without changing logic. That is the true power of the Liskov substitution principle. According to LSP, a child class should be able to replace its parent class without breaking the system or causing unexpected behavior. Left side, LSP violation, wrong design. Here we have a bird base class that has a fly method. A penguin class inherits from bird, but penguins cannot fly. So inside the overridden fly method, the penguin throws an exception saying cannot fly. Now the problem is, if we write bird equals new penguin bird.fly, this causes a runtime error, because the system expected every bird to be able to fly, but penguin broke that expectation. This means, child class changed expected behavior, subclass cannot safely replace parent, system becomes unpredictable, so this clearly violates the Liskov substitution principle. Right side, LSP adherence, correct design. On the right side, we fix the design. Instead of forcing all birds to fly, we create an interface. For example, flyable right pointing arrow contains fly method. Now only birds that can actually fly implement this interface. So sparrow implements flyable and provides a valid flying behavior. Penguin does not implement this interface because it cannot fly, so no wrong behavior occurs. Now when we write flyable flyer equals new sparrow flyer.fly, it works perfectly and predictably. This means correct behavior, safe substitution, no surprises, code is clean and logical. Core message: do not force child classes to support behaviors they logically cannot do. Design your hierarchy so that every subclass truly follows and respects the expectations of its parent type. That is the true meaning of the Liskov substitution principle. Notification systems. Liskov substitution principle. Consider applications that send notifications. At first, they may support only email notifications. Later, requirements come to add SMS, then push notifications, then WhatsApp alerts, and many more in the future. All these notification types usually inherit from a base notification class or implement a common notification interface. Now, according to the Liskov substitution principle, anywhere the system expects a base notification type, we should be able to substitute it with any notification subclass such as email, SMS, push, or WhatsApp, and the application should still work correctly without breaking or behaving unexpectedly. LSP violation. On the left side, imagine a bad design where subclasses do not behave as the base notification class promises. For example, the base class may define a send message method, but one subclass limits functionality, changes expected behavior, throws unexpected errors, or doesn't properly support the contract. This results in unpredictable system behavior, failures when switching notification types, bugs when different notification implementations are used, fragile and unreliable design. This clearly violates the Liskov substitution principle, because subclasses cannot safely replace the parent class. LSP done correctly. Now look at the correct design. We define a clear and stable notification interface or base class with a method like send message. Every notification type, email notification, SMS notification, push notification, and WhatsApp notification, follows the same contract, same expectations, and same logical behavior. They don't surprise the system. They don't break functionality. They respect the rules defined by the parent. So now, any notification subclass can be safely substituted, the system continues to work smoothly, behavior remains consistent and predictable, the design becomes professional, stable, and future-ready. Core meaning of LSP here: if the system expects a notification, you should be able to provide any valid notification subclass, and everything should still work correctly without breaking, without changing logic, and without unexpected behavior. That is the true power of the Liskov substitution principle. This image explains how the Liskov substitution principle, LSP, applies to a notification system. According to LSP, a subclass must be able to replace its parent class without causing errors or changing expected behavior. Left side, LSP violation, bad design. On the left side, we have a base class. Notification base right pointing arrow contains a send message method. Then we have a subclass. SMS notification inherits from notification base. But inside this subclass, the send method behaves differently. If the message length is greater than 10 characters, it throws an exception. If message length greater than 10, throw new exception, message too long for SMS. Now if the client writes notification base notify equals new SMS notification, notifier, send, this is a very long message. the system crashes with a runtime error, because the system expected normal sending behavior but instead received an unexpected exception. This leads to unpredictable system behavior, runtime failures, subclass breaking parent contract. So this clearly violates the Liskov substitution principle, because the subclass cannot safely substitute the parent. Right side, LSP adherence, good design. On the right side, the design is corrected. Instead of forcing behavior through inheritance, we create an interface. iNotification right pointing arrow defines send message method. Then, email notification implements iNotification, SMS notification implements iNotification. But now the SMS class handles long messages safely instead of throwing exceptions. If the message is too long, it simply truncates it. If message length greater than 10, message equals message substring 0, 10 plus. So when the client calls, iNotification notify equals new SMS notification, notifier, send. This is a very long message. It works smoothly and predictably. This results in safe and consistent behavior, no runtime surprises, robust and reliable system. Subclass fully follows parent contract. Final message, LSP ensures that subclasses can be used anywhere their parent is expected, without breaking the system, without changing logic, and without unexpected behavior. That's what makes the system predictable, stable, and professional. Tax calculations and business rules, Liskov substitution principle. In banking, finance, or government systems, tax rules and business policies frequently change. Different types of tax rules may exist, such as income tax, GST, VAT, surcharge rules, and yearly policy-based taxes. These tax modules usually inherit from a base tax rule class or implement a common tax rule interface. According to the Liskov substitution principle, anywhere the system expects a base tax rule, we should be able to safely substitute it with any tax subclass like GST tax rule, income tax rule, or new tax rule 2024, and the system should still work correctly without failures or unexpected behavior. LSP violation. Now imagine a bad design where subclasses do not behave consistently with the base tax rule. For example, the base class defines a calculate income method with expected behavior, but one subclass changes the meaning of calculation, restricts valid inputs, throws unexpected exceptions, or produces logically inconsistent results. This leads to serious problems. System becomes unpredictable, tax calculations become unreliable, errors occur when switching between tax rule implementations, maintenance becomes risky and confusing. This clearly violates the Liskov substitution principle, because child tax rule classes cannot safely replace the base tax rule. LSP done correctly. In the correct professional design, we define a stable tax rule interface or base tax class with a clear contract like calculate income. Every tax rule such as GST tax rule, income tax rule, or new tax rule 2024 must follow the same input expectations, the same logical meaning of calculation, the same behavioral consistency. They do not surprise the system or change the fundamental expectation of what a tax calculation means. So now, any tax subclass can replace the base class safely, the system behaves consistently, calculations remain trustworthy, design becomes stable, maintainable, and professional. Core meaning of LSP here: if the system expects a tax rule, you should be able to plug in any valid tax rule subclass, and everything should still work correctly without breaking calculations or changing system behavior. That is the real power of the Liskov substitution principle in financial and enterprise systems. That is the real power of the Liskov substitution principle in financial and enterprise systems. Now let's understand the Liskov substitution principle using a tax calculation system example. On the left side, we see a bad design that violates LSP. We have a base class called tax rule base with a calculate income method. It calculates tax safely for valid income values. But then we create a subclass called surcharge rule, and instead of behaving like the parent class, it completely changes the behavior. If income is greater than 10 lakh, it throws an exception saying, income too high for surcharge. So when the client writes, tax rule base rule equals new surcharge rule, calculate 15000, the application crashes at runtime. This is unpredictable system behavior, because the parent class never promised such an exception. The subclass broke the contract, so it violates the Liskov substitution principle. Now look at the right side. This is the correct LSP compliant design. Instead of forcing everything through inheritance, we define a stable interface called I-tax rule with a calculate income method. Different tax rules like GST tax rule and new tax rule 2024 implement this interface and provide their own calculation logic. Without breaking expectations, even if income is very high, they handle it safely and logically instead of throwing unexpected exceptions. So when the client writes, I tax rule equals new tax rule 2024, rule, calculate 150000, it works perfectly and returns a valid tax value. This results in predictable behavior, stable system, no runtime surprises, clean and professional design. Core meaning, LSP ensures that subclasses or implementations can be used anywhere their parent type is expected, without breaking the application or changing its expected behavior. That's what makes the system reliable, safe, and enterprise-ready. Logging systems, Liskov substitution principle. In many applications, logging may initially be done using a simple file logger. Later, requirements grow. We may need to log to a database, a cloud service, or a monitoring tool like Elk, Splunk, or Application Insights. All of these logging components usually inherit from a base logger class or implement a logger interface. According to the Liskov substitution principle, anywhere the system expects a logger, we should be able to use any logger subclass, file logger, DB logger, or cloud logger, and the system should still work perfectly without errors, unexpected behavior, or modifications. LSP violation, wrong approach. Imagine a bad design where some logging subclasses do not behave like the parent logger class. For example, the base class defines a log, message, method, but one logger throws unexpected exceptions, changes how logging works, restricts the message format, or behaves unpredictably. This leads to unstable logging, crashes or failures during substitution, bugs when switching logger types, hard to maintain system. This clearly violates the Liskov substitution principle, because these subclasses cannot safely replace the base logger. LSP done correctly, in the correct design, we define a clear and stable logger interface or base logger class with a contract like log, message, every logger, file logger, database logger, cloud logger, monitoring logger, must follow the same expectations, maintain consistent behavior, not break functionality, not surprise the system. So now, any logger subclass can safely replace the base logger. The system remains predictable and reliable. Logging can switch easily without breaking anything. The application becomes professional and future ready. Core meaning of LSP here: if the system expects a logger, you should be able to substitute any logger subclass, and the application should continue working correctly, without breaking, without modifying the system, and without unexpected behavior. That is the true power of the Liskov substitution principle in logging systems. Now let's talk about the advantages of the Liskov substitution principle and why it is so powerful in real-world software development. First, it makes our code stable and reliable. When subclasses truly behave like their parent classes, the system remains predictable. We can substitute child objects confidently without fear of breaking existing features. Second, it ensures behavioral consistency. LSP guarantees that whenever we replace a base class with a derived class, everything still works correctly. This avoids surprises, unexpected behavior, and runtime failures. Third, it improves maintainability. Systems built with LSP are cleaner, logically structured, and easier to maintain. Developers can extend functionality safely without worrying that a subclass will break existing logic. Fourth, it supports scalability and reusability. When subclasses follow proper behavior, they can be reused across different parts of the system or even across multiple applications, reducing rework and development effort. Fifth, it encourages good design and professional inheritance usage. LSP prevents misuse of inheritance. It forces developers to think carefully about design, contracts, and responsibilities instead of blindly inheriting and overriding methods. In simple words, the Liskov substitution principle helps us build robust, predictable, maintainable, and enterprise-grade applications, where child classes truly act as safe substitutes for parent classes. Disadvantages, limitations of LSP. Now let's talk honestly. Even though the Liskov substitution principle is powerful, it also has some disadvantages and challenges developers must understand. First, it requires strong design understanding. Beginners may struggle to design subclasses that perfectly follow the parent's behavior, which may lead to accidental violations. Second, it can sometimes feel restrictive. Developers may feel limited because subclasses must strictly follow the parent contract. Any deviation can lead to design rework. Third, it can make inheritance complex if misused. If teams overuse inheritance just to apply LSP, it can complicate class hierarchies instead of simplifying them. Fourth, it may require redesign when violated. If an existing system violates LSP, fixing it may involve refactoring, introducing interfaces, or replacing inheritance with composition, which requires effort. Finally, it may be unnecessary for very small or simple systems. For small projects with minimal inheritance, applying strict LSP rules may feel like over-engineering. So while LSP is extremely valuable, it should be applied thoughtfully, ensuring inheritance truly makes sense in the design. Liskov substitution principle in microservice architecture. Now let's understand how the Liskov substitution principle fits in microservice architecture and why it is important in modern cloud-based systems. In microservices, different services often implement common contracts or follow similar behaviors. For example, payment service variants, notification service variants, authentication service variants, etc. Here, LSP ensures that whenever a service or its implementation is replaced, upgraded, or versioned, it should behave correctly without breaking consuming systems. If service v1 is replaced with service v2, clients should still work smoothly. This is LSP at a microservice level. For example, if you replace a basic email notification service with a more advanced one, or payment service v1 with payment service v2, they should still respect the same API contract, behavior, and expectations. If not, systems break, clients fail, and integrations collapse, meaning LSP is violated. When applied correctly in microservices, LSP provides better reliability, safer upgrades and versioning, smooth backward compatibility, confidence while replacing or enhancing services. However, we must also be careful. Too many inconsistent implementations or poorly designed APIs can break LSP and increase complexity. So LSP should be applied with strong contract design, API stability, versioning strategy, and architectural discipline. In short, LSP ensures that any subclass or service implementation can safely replace its parent or contract without breaking the system, making applications stable, scalable, and truly professional. So that brings us to the end of this powerful session on the Liskov substitution principle. We learned what LSP is, why it is important, where it is used, how it works in real-world systems, practical examples, advantages, disadvantages, and how it helps us build reliable and professional software. If you truly understand this principle and start applying it in your projects, your code will become more stable, more predictable, easier to maintain, and truly enterprise-ready. Remember, great developers don't just write classes, they design behaviors that remain consistent and trustworthy, no matter which implementation is used. If you found this video helpful, make sure to like the video, subscribe to the channel, and share it with your developer friends. Drop your thoughts, doubts, or topics you want next in the comments. I'd love to help you learn more. Thank you so much for watching. This is Vidyaskatra channel, helping you become a smarter and stronger developer. See you in the next video. Until then, keep learning and keep coding. Rocket.
Welcome to Vidyakshetra YouTube channel, a dedicated place for developers, learners, and professionals to upgrade their knowledge with real-world concepts and practical explanations. Hey developers, welcome back to the channel. In today's session, we are going to unlock one of the most important principles in clean coding and professional software development, the interface segregation principle. If you've ever dealt with messy interfaces, classes forced to implement unnecessary methods, confusion during maintenance, or bugs appearing because of overloaded interfaces, then this video is absolutely for you. Today, I'm going to explain the interface segregation principle in the simplest way possible with real examples, real coding scenarios, and crystal clear explanations so you can confidently apply it in your projects. Watch till the end. Once you understand ISP properly, your object-oriented design skills and architecture thinking will completely transform. Let's begin. Now let's understand the official definition of the interface segregation principle. The interface segregation principle states that no client should be forced to depend on interfaces it does not use. In simple words, an interface should not be big and overloaded with many unrelated methods. Instead of one fat interface, we should create multiple small, focused, and meaningful interfaces. A class should only implement what it actually needs, not unnecessary methods that lead to dummy implementations, empty methods, or exceptions. By following ISP, we ensure our interfaces are clean, purpose-driven, easy to understand, easy to maintain. It prevents us from creating God interfaces that try to do everything and force subclasses to handle things they don't care about. Why is the interface segregation principle important? Because in real-world software development, requirements continuously evolve and systems grow over time. If interfaces are large and tightly coupled, any change in one part of the interface can break multiple classes, even if they don't use that feature. This creates unnecessary dependencies, makes testing harder, and increases maintenance headaches. Violating ISP leads to bloated and confusing interfaces, classes implementing unnecessary methods, more bugs when interfaces change, tight coupling, and fragile designs. But when we follow ISP, our code becomes more predictable, more stable, easier to maintain, safer to extend. Developers can build only what is needed without being forced to depend on extra, irrelevant functionality. This leads to cleaner design, better architecture, and truly professional quality software. In simple words, the interface segregation principle helps us build professional, reliable, and maintainable applications by ensuring that classes only depend on the features they actually need. Instead of forcing classes to implement unnecessary methods, ISP encourages us to design small, focused, and meaningful interfaces. This keeps our code clean, logical, and trustworthy in real-world projects. Where do we use the interface segregation principle in real life? We apply ISP anywhere. Systems need different functionalities for different clients or modules. This includes areas like payment processing, notification systems, user management, tax and business rules, reporting modules, IoT devices, API design, and microservices. Whenever different components need different behaviors, ISP ensures that each one only implements what it truly requires, nothing extra. You'll see ISP heavily used in enterprise software, banking applications, e-commerce platforms, scalable architectures, and modern frameworks, where stability and flexibility are extremely important. Whenever we know that different modules require different capabilities, that's the perfect place to apply the interface segregation principle. In short, we use ISP wherever we want clarity, flexibility, and low coupling in our software. We apply ISP by making sure interfaces are not too big or overloaded. Instead of creating one large God interface with many unrelated methods, we split it into multiple smaller role-based interfaces, so each class implements only what it needs. That means classes should not be forced to implement unused methods. No dummy methods, no empty implementations, no unnecessary dependencies. Instead of blindly designing giant interfaces, we think carefully. If one interface feels overloaded, we break it into smaller ones. If a component needs a special behavior, we design a separate, focused interface for it. If a class cannot reasonably support an interface method, that method does not belong there. To achieve this, we follow ideas like focused responsibilities, clear contracts, meaningful, purpose-driven interfaces, avoiding extra burden on clients. In many systems, we use ISP together with abstraction, composition, dependency inversion, and clean architecture, ensuring the system remains stable, predictable, and easy to maintain. We apply the interface segregation principle by designing small, well-defined interfaces so that each class depends only on what it truly needs. Nothing more, nothing less. This prevents surprises, reduces bugs, and helps us build clean, scalable, and truly professional software. Let's now look at some real-world practical examples where the interface segregation principle is actually used in the software we use every day. Payment systems. Think about e-commerce platforms like Amazon, Flipkart, or any online shopping website. They support different payment experiences such as online payments, wallet payments, installment, EMI payments, refund processing. Now, instead of creating one huge payment interface with every possible method, like pay, refund, EMI process, wallet recharge, generate QR code. ISP says, don't force every payment class to implement all these methods, because not every payment method supports everything. ISP violation, wrong approach. In a bad design, we create one fat interface like iPayment with too many methods. Then classes like credit card payment, UPI payment, PayPal payment are forced to implement methods they don't need, leading to dummy method. Implementations, empty methods, throwing not supported. Exceptions, confusing, bloated, and risky code. This clearly violates the interface segregation principle because clients depend on methods they do not use. ISP done correctly, right approach. In the correct design, we break the big interface into multiple small focused interfaces, such as iPayment, iRefundable, IMI support, iWallet feature. Now, credit card payment implements iPayment plus iRefundable UPI. Implements iPayment, wallet implements iPayment plus iWallet feature. EMI services implement IMI support. This way, each class implements only what it needs, no useless or empty methods. System becomes cleaner and easier to maintain. Instead of a bird flying problem for LSP, here ISP fits beautifully in the same concept. ISP violation. We create one interface, iBird, fly, walk, swim. Now every bird must implement fly, walk, and swim. But sparrow cannot swim. Penguin cannot fly. Ostrich cannot fly. So developers end up writing empty methods, not supported exceptions, meaningless implementations. This violates ISP because these birds are being forced to depend on behaviors they don't need. ISP done correctly. We redesign using small, focused interfaces. iBird, iWalkable, iFlyable, iSwimmable. Now Sparrow implements iBird plus iFlyable. Penguin implements iBird plus iSwimmable. Ostrich implements iBird plus iWalkable. This gives correct behavior. No forced methods. Cleaner architecture. Zero unnecessary dependencies. Do not create giant interfaces that force classes to implement things they don't need. Instead, split them into small, meaningful role-based interfaces so every class uses only what is required. That is the true power of the interface segregation principle. Consider applications that send notifications. At first, they may support only email notifications. Later, requirements come to add SMS, then push notifications, then WhatsApp alerts, and many more in the future. Now, instead of creating one big notification interface with every possible method like send email, send SMS, send push, send WhatsApp. The interface segregation principle says, don't force every notification class to implement all these methods. A class should only depend on the features it actually needs. ISP violation. Wrong design. In a bad design, we create a single, large, God interface like iNotification, send email, send SMS, send push, send WhatsApp. Then, Email notification is forced to implement SMS and WhatsApp methods. SMS notification is forced to implement push and email methods. Push notification is forced to implement WhatsApp and email methods. So developers end up writing empty methods, dummy implementations, not supported exceptions. Confusing and fragile design. This clearly violates the interface segregation principle because classes are forced to depend on methods they do not need. ISP done correctly. Right design. Now let's look at the correct ISP compliant approach. Instead of one large interface, we create small focused interfaces such as IEmail notification, send email message, ISMS notification, send SMS message, IPUSH notification, send PUSH message, IWHATSAPP notification, send WhatsApp message. Now, email notification implements only IEmail notification, SMS notification, implements only ISMS notification, push notification implements only iPush notification, WhatsApp notification implements only WhatsApp notification. This gives clean and meaningful interfaces, no unnecessary methods, no runtime surprises, easy to maintain and extend. Practical behavior. Example: if SMS has limitations like shorter message length, it can handle the behavior internally, truncate, split message, etc., without being forced to implement unrelated features like email or push. No empty methods, no forced features, no broken contracts. Everything is structured, logical, and predictable. Core meaning of ISP. Here, do not create large interfaces that force classes to depend on unnecessary features. Create small, role-based interfaces so each class implements only what it truly needs. That's the true power of the interface segregation principle. It keeps systems clean, modular, stable, predictable, and professional. Consider applications that send notifications. At first, they may support only email notifications. Later, requirements come to add SMS, then push notifications, then WhatsApp alerts, and many more in the future. Now, instead of creating one big notification interface with every possible method like send email, send SMS, send push, send WhatsApp. The interface segregation principle says, don't force every notification class to implement all these methods. A class should only depend on the features it actually needs. ISP violation. Wrong design. In a bad design, we create a single, large, God interface like iNotification, send email, send SMS, send push, send WhatsApp. Then, email notification is forced to implement SMS and WhatsApp methods. SMS notification is forced to implement push and email methods. Push notification is forced to implement WhatsApp and email methods. So developers end up writing empty methods, dummy implementations, not supported exceptions. Confusing and fragile design. This clearly violates the interface segregation principle because classes are forced to depend on methods they do not need. ISP done correctly. Right design. Now let's look at the correct ISP compliant approach. Instead of one large interface, we create small focused interfaces such as IEmail notification, send email message, ISMS notification, send SMS message, IPUSH notification, send PUSH message, IWHATSAPP notification, send WhatsApp message. Now, email notification implements only IEmail notification, SMS notification, implements only ISMS notification. Push notification implements only iPush notification. WhatsApp notification implements only WhatsApp notification. This gives clean and meaningful interfaces, no unnecessary methods, no runtime surprises, easy to maintain and extend. Practical behavior. Example: If SMS has limitations like shorter message length, it can handle the behavior internally, truncate, split message, etc., without being forced to implement unrelated features like email or push. No empty methods, no forced features, no broken contracts. Everything is structured, logical, and predictable. Core meaning of ISP. Here, do not create large interfaces that force classes to depend on unnecessary features. Create small, role-based interfaces so each class implements only what it truly needs. That's the true power of the interface segregation principle. It keeps systems clean, modular, stable, predictable, and professional. In banking, finance, or government systems, tax rules and business policies frequently change. There may be different types of tax-related behaviors, such as income, tax calculation, GST calculation, VAT calculation, surcharge processing, yearly policy-based rules. Now, instead of forcing every tax module to support all these behaviors through one giant interface, the interface segregation principle says, don't create one big God interface like iTax rule, calculate income tax, calculate GST, calculate VAT, apply surcharge, process yearly policy. Because not every tax module needs all of these. Each rule has a different purpose and different logic. ISP violation, wrong design. In a bad design, developers create one large interface and force every tax class to implement unnecessary methods. For example, income tax rule is forced to implement GST logic. GST tax rule is forced to handle yearly policies. VAT tax rule is forced to handle surcharges. This leads to dummy method implementations, empty methods not supported, exceptions, confusing and tightly coupled code, unnecessary complexity and maintenance headaches. This clearly violates the interface segregation principle because classes are being forced to depend on methods they do not need. ISP done correctly. Right design. In the correct professional design, instead of one fat interface, we create multiple small focused interfaces, such as iIncome tax rule, calculate income tax income, IGST tax rule, calculate GST amount, VAT tax rule, calculate VAT amount, I surcharge rule, apply surcharge amount, I policy, tax rule, apply policy year, income. Now, income tax rule implements only iIncome tax rule. GST tax rule implements only IGST tax rule. VAT tax rule implements only IV tax rule. Surcharge rule implements only I surcharge rule. New policy tax rule implements I policy tax rule. This gives clean separation of responsibilities, no unnecessary dependencies, no empty or fake methods, easy to maintain and extend, clear, meaningful design, practical behavior. Example, if tomorrow government introduces new tax rule, 2025, we simply create a new interface or class aligned to its behavior instead of modifying every existing tax class. Each module knows only what it needs to know, nothing more. Core meaning of ISP. Here, if a system deals with multiple behaviors, do not force every class to implement all of them. Split features into small role-based interfaces, so each tax rule implements only what it actually needs. That is the real power of the interface segregation principle, especially in financial and enterprise systems, where clarity, flexibility, and maintainability are extremely important. Plugin-based applications like VS Code, browsers, IDEs, and game engines allow users to install different plugins, such as themes, extensions, and developer tools. All these plugins are built on top of a plugin contract provided by the main system. Now, according to the interface segregation principle, plugins should not be forced to implement features they do not need. If we design one giant interface like iPlugin, load, execute, debug, track usage, save settings. Then every plugin must implement everything, even if it doesn't need debug or tracking. This creates unnecessary complexity and tightly coupled code. ISP violation, wrong approach. Imagine a system where theme plugins are forced to implement execution logic. Simple extensions are forced to support debugging. Lightweight plugins must implement tracking features they don't need. This leads to dummy methods, not supported, exceptions, confusing, design hard to maintain system. This clearly violates the interface segregation principle because plugins are forced to depend on methods they don't use. ISP done correctly, right approach. In a professional design, we split the plugin contract into multiple small interfaces, such as iBase plugin, load, unload, iRunnable plugin, execute, iDebuggable, debug, iTrackable, track usage. Now, theme plugins implement only load, unload. Tool plugins implement, execute. Advanced plugins may implement debug or tracking. This ensures clean separation of responsibilities, no unnecessary features, flexible extension model, stable and predictable behavior. Decor. Meaning of ISP. Here. If the system supports plugins, give each plugin only the interfaces it actually needs, instead of forcing every plugin to implement everything. That is the true power of the interface segregation principle in plugin architectures. In many applications, logging may start with a simple file logger. Later, requirements grow. We need database logging, cloud logging, monitoring tools like ELK or Splunk, and more. A bad design mistake is creating one massive logger interface like iLogger, log2 file, log2 database, log2 cloud, log2 monitoring. Now every logger is forced to implement all methods, even if it doesn't support them. ISP violation, wrong approach. This results in empty dummy methods, not supported exceptions, rigid implementation, difficult maintenance. This clearly violates ISP because every logger is forced to depend on unnecessary functionality. ISP done correctly, right approach? Instead, we design small, focused interfaces. iFile logger, stations log2 file, message. iDatabase logger, log2 database, message. iCloud logger, log2 cloud, message. iMonitoring logger, module log2 monitoring, message. Now, file logger implements iFile logger. Database logger implements IDATABASELOGGER cloud. LOGGER implements ICLOUD monitoring. LOGGER implements IMONITORING LOGGER. This gives clean and meaningful design, zero unnecessary dependencies. Easy testing and extension. Highly maintainable logging system. Core meaning of ISP. Here, if the system expects logging, don't force one logger to handle everything. Give each logger only the responsibilities it truly needs. That is the true power of the interface segregation principle in logging systems. Now let's talk about the advantages of the interface segregation principle and why it is so powerful in real-world software development. First, it makes our code clean and maintainable. Since classes implement only the methods they actually need, we avoid unnecessary complexity, empty methods, and confusing code. The design becomes easier to understand and maintain. Second, it reduces unnecessary dependencies. ISP ensures that classes are not forced to depend on features they don't use. This keeps components lightweight, less coupled, and easier to modify without affecting unrelated parts of the system. Third, it improves flexibility and scalability. When new features are added, We can simply introduce new small interfaces without breaking existing ones. This allows systems to evolve smoothly as requirements grow. Fourth, it enhances stability and reduces bugs. Because interfaces are smaller and more focused, changes in one area don't accidentally break other components. This increases reliability and makes systems safer to enhance. Fifth, it promotes professional design thinking. ISP forces developers to clearly think about responsibilities and roles instead of dumping everything into one massive interface. This leads to cleaner architecture and better long-term code quality. In simple words, the interface segregation principle helps us build clean, modular, predictable, and enterprise-ready applications, where every component gets exactly what it needs, nothing more, nothing less. Disadvantages, limitations of ISP. Now let's be honest, even though ISP is powerful, it also has some challenges developers should understand. First, it requires good design understanding. Beginners may find it difficult to decide how to split interfaces correctly, which may lead to over-segmentation or wrong abstractions. Second, it may increase the number of interfaces. Since we split big interfaces into many smaller ones, the number of files and contracts increases. Without proper organization, this can feel overwhelming. Third, it can be misused. If developers over-apply ISP and create extremely tiny interfaces without real need, the design may become fragmented and confusing rather than helpful. Fourth, refactoring may be required in existing systems. If a legacy project has fat interfaces, applying ISP means redesigning, restructuring, or rewriting parts of the system, which takes time and effort. Finally, it may feel unnecessary for very small projects. For small or single-purpose systems, too many segregated interfaces may feel like over-engineering. So while ISP is extremely valuable, it should be applied thoughtfully, with proper planning and architectural understanding. Interface segregation principle in microservice architecture. Now let's understand how the interface segregation principle fits into microservice architecture and why it is very important in modern cloud-based systems. In microservices, each service is designed to handle a specific responsibility. For example, payment service, notification service, reporting service, user service, and so on. According to ISP, each service should expose small, focused, purpose-driven APIs, not one giant API that forces clients to depend on unnecessary operations. Clients should only consume what they actually need. For example, a simple consumer may only need a basic send notification. API and admin tool may need analytics APIs. A monitoring tool may need health check APIs. Instead of one huge interface, we create separate endpoints or contracts for each responsibility. This prevents consumers from dealing with unnecessary data and unwanted functionality. When applied correctly, ISP in microservices provides better reliability, clear and focused service contracts, easier upgrades without breaking clients, safer evolution of APIs, cleaner and more modular architecture. However, if services expose large all-in-one APIs, they become tightly coupled, harder to change, and risk breaking multiple consumers at once, clearly violating ISP. The interface segregation principle ensures that every class, module, or service depends only on what it truly needs. This makes software clean, modular, maintainable, scalable, and truly professional. Great! Here is your fully updated closing section, rewritten for the Interface Segregation Principle, ISP, while keeping the same tone, flow, and powerful YouTube narration style. However, we must also be careful. Creating too many unnecessary or poorly designed interfaces can increase complexity and confusion. If interfaces are badly split, projects may end up with fragmented responsibilities instead of clean design. So the interface segregation principle should always be applied with clear responsibility design, meaningful boundaries, and proper architectural discipline. In short, the interface segregation principle ensures that every class, module, or service depends only on the functionality it truly needs, helping us build clean, modular, flexible, and extremely maintainable applications. So that brings us to the end of this powerful session on the interface segregation principle. We learned what ISP is, why it is important, where it is used, how it works in real-world systems, practical examples, advantages, disadvantages, and how it helps us build reliable and professional software. If you truly understand this principle and start applying it in your projects, your code will become cleaner, easier to maintain, more scalable, and truly enterprise-ready. Remember, great developers don't just create interfaces. They design meaningful contracts that provide exactly what is needed. Nothing more, nothing less. If you found this video helpful, make sure to like the video, subscribe to the channel, and share it with your developer friends. Drop your thoughts, doubts, or the next topic you want in the comments. I'd love to help you learn more. Thank you so much for watching. This is Vidaiskatara channel, helping you become a smarter and stronger developer. See you in the next video. Until then, keep learning and keep coding. Hey developers! Welcome back to Vidaiskatara YouTube channel, your dedicated space to learn real-world software engineering concepts in the most practical and crystal clear way. Today, we are going to dive deep into one of the most powerful pillars of SOLID Principles, the dependency inversion principle. If you want to become a professional developer, write clean architecture, build scalable applications, and design enterprise-level systems, then this principle is absolutely essential for you. Let's start with a question. Have you ever worked on a project where changing something small in one place suddenly broke multiple areas of the application? Or have you seen code where one class is directly dependent on another class, and because of these tight connections, even a small modification becomes risky? Maybe you wanted to switch databases, change a payment gateway, replace an email service, or update a logging library. But as soon as you tried to change it, everything started crashing. If you faced these situations, then what you actually experienced was the absence of dependency inversion. Dependency inversion is a principle that helps us break tight coupling between software modules. In simple words, it helps us design software where high-level modules do not directly depend on low-level modules. Instead, both of them depend on abstractions like interfaces or abstract classes. The principle also says that abstractions should not depend on details, but details should depend on abstractions. This may sound slightly technical at first, but don't worry. By the end of this video, you'll not only understand it clearly, but you'll also be able to apply it confidently in your real projects. Let's break it down in the simplest way possible. In every project, we have high-level modules and low-level modules. High-level modules usually contain our business logic, the most important part of the application. Low-level modules handle specific operational tasks like database communication, payment gateway integration, notification services, logging, API calls, etc. Normally, in traditional poor design, we directly connect high-level modules with low-level modules. For example, your business logic might directly call a specific database class or directly use a Razorpay class for payment. Initially, this may look simple, but the real problem appears when requirements change. Imagine this scenario. Your business layer is directly connected to SQL Server. After a few months, your client says, "We want to migrate to MongoDB." Now what happens? You are forced to touch your business logic, rewrite code, modify multiple places, risk introducing bugs, and spend unnecessary effort. This becomes even worse when many modules depend on that same database. The same problem happens when you want to replace a payment gateway, logging library, email provider, SMS service, cloud storage, or any other dependency. This kind of coding style locks your system, restricts flexibility, and creates long-term pain. That is why dependency inversion exists. It protects high-level business logic from frequent changes. Instead of directly connecting to low-level concrete classes, we introduce an abstraction layer. This abstraction is usually an interface or an abstract class. The high-level module depends on that abstraction, and the low-level module implements it. Now the magic happens. Your business logic no longer cares which implementation is behind it. Whether you use SQL, MongoDB, Oracle, Razorpay, Stripe, PayPal, or any other system, the business logic remains untouched. Only implementation changes. That's the power of dependency inversion. Let's understand this using a real-life analogy. Think about electrical appliances in your home. Your fan, TV, refrigerator, washing machine. None of them are directly hardwired to electricity. Instead, they are designed to connect using a standard plug. The wall socket acts as a standard interface. Electricity providers can change, wiring may change, infrastructure may upgrade, but your appliances still work because they depend on the interface, not the internal wiring system. This is exactly what dependency inversion does in software architecture. It creates a stable contract that both high-level and low-level modules follow. Now let's relate this to programming. Suppose you have a payment service used in your application. A beginner developer might directly write code like payment service depends on Razorpay class. This works initially, but now suppose your client says, "We want Stripe." Suddenly you must go into business logic and change everything. But a professional developer creates an abstraction first, like iPayment Gateway. Razorpay implements it, Stripe implements it, and any future payment system can also implement it. Now payment service depends only on iPayment Gateway. Now payment service depends only on iPayment Gateway. Tomorrow, if you want to change Razorpay to Stripe, you don't even touch payment service. You only swap the implementation. This is dependency inversion in action. This principle is deeply connected to modern software engineering. Frameworks like ASP.NET Core, Spring Boot, Angular, Nest.js, Node.js architectures, and enterprise systems completely rely on dependency inversion. The reason is simple. Professional software development is not about just writing working code. It's about writing maintainable, scalable, testable, and future-proof code. Projects live for years. Requirements change regularly. Technology upgrades continuously. Without DIP, your project becomes rigid and fragile. Another major advantage of dependency inversion is testability. When your classes depend directly on concrete implementations, unit testing becomes a nightmare. You can't easily mock dependencies. You often end up depending on real database connections or real APIs during tests, which is slow and risky. But when you depend on interfaces, testing becomes super easy. You can create mock implementations, inject fake services, simulate behaviors, and test your business logic independently. That's why every professional testing framework and dependency injection container is designed with this principle in mind. Another important thing to understand is that dependency inversion is not just a coding pattern, it's a design mindset. It forces you to think in a structured, layered, and decoupled way. When you start designing your system, don't think about implementations first. Think about behavior, think about contracts, think about what your system needs to do, not how it will do it initially. Once you define clear abstractions, implementations can change any time without affecting the main system. This is the foundation of clean architecture, onion architecture, hexagonal architecture, and many enterprise patterns. Now let's talk about the impact of dependency inversion in real projects. When applied correctly, it significantly reduces code complexity. You no longer fear changing things. You don't break existing modules when enhancing features. Teams can work independently. One team can handle business logic while another team works on infrastructure because both meet at the abstraction level. This also improves collaboration, modularity, reusability, and long-term stability of the software. But remember, dependency. Inversion must be applied carefully. Don't create unnecessary abstractions just for the sake of it. Use it where dependencies genuinely exist, especially in places where change is expected or when you deal with external systems. The goal is to keep your core system stable while allowing implementations to evolve freely. So to conclude, always remember this simple understanding. Never let your important business logic depend directly on concrete classes. Let both business logic and implementations depend on abstractions. When you design systems with dependency inversion, your applications become cleaner, smarter, flexible, maintainable, and truly professional. If you found this explanation helpful and easy to understand, make sure to like the video, share it with your developer friends, and subscribe to Vidaiskatara YouTube channel for more powerful, real-world software engineering content. This is your guide to becoming a smarter, more confident, and industry-ready developer. Thanks for watching, and see you in the next session. Hey developers, welcome back to the channel. In today's session, we are going to understand one of the most powerful concepts in professional software design, the dependency inversion principle. And instead of just learning definitions, we are going to understand it through clear, real-world examples that you actually experience every single day in modern applications. Let's start with something very familiar. Payment systems. Think about popular e-commerce platforms like Amazon, Flipkart, or any online shopping website. These platforms support a wide variety of payment experiences, such as credit and debit card payments, UPI payments, wallet transactions, EMI or installment payments, and of course, refund processing. Now, imagine for a moment that the main business logic of this e-commerce platform directly depends on a specific payment provider like Razorpay, Stripe, or PayPal. That means the business code is tightly connected to a specific payment class. Now, what happens if one day the company decides to replace Razorpay with Stripe? Or maybe they want to introduce PayPal support? Or they want to modify how EMI processing works. Every time such a change happens, developers are forced to modify the business logic again and again. This creates dependency chains, increases risk, introduces bugs, and makes the application hard to maintain, hard to scale, and difficult to test. This situation clearly violates the dependency inversion principle, because here the high-level business layer directly depends on the low-level payment implementation. So what is the correct approach? Dependency inversion principle says that high-level modules should not depend on low-level modules. Both should depend on abstractions. And also, abstractions should not depend on details, but details should depend on abstractions. That simply means your business logic should not directly depend on Razorpay, Stripe, or any specific service. Instead, both the business layer and the payment services should depend on a common abstraction. So instead of directly connecting payment service with Razorpay or Stripe, we introduce an abstraction layer, something like an iPayment Gateway interface. Now Razorpay implements iPayment Gateway. Stripe implements iPayment Gateway. PayPal implements iPayment Gateway. Any future payment provider can also implement it. Now your business layer only talks to the iPayment Gateway abstraction, not the actual payment provider. So tomorrow, if you want to switch from Razorpay to Stripe, or if you want to add PayPal, you don't need to touch the business logic at all. You simply plug in a new implementation. That is the beauty and power of dependency inversion. It brings flexibility, maintainability, and future readiness to your software. Let's move to another real-world example: notification systems. Think about applications that send notifications every day, such as email alerts, SMS messages, WhatsApp notifications, or push notifications. In a poor design, the main system directly depends on email service, SMS service, or push notification service. This means the business logic is directly tied to specific implementations. Now, if the organization decides to integrate a new notification channel or replace an existing provider, once again, developers are forced to modify the business layer, which is risky and inefficient. But when we apply the dependency inversion principle, the design completely changes. Instead of depending on these specific services, we create an abstraction like iNotification service. Now email service implements it, SMS service implements it, push service implements it, and any future notification service can also implement it. The business logic simply depends on iNotification service, the abstraction, so we can easily add new services, replace existing ones, and modify implementations without disturbing the core system. The design becomes clean, scalable, modular, and extremely testable. To understand the thinking behind dependency inversion even better, imagine a conceptual scenario. Instead of designing systems that depend on concrete objects directly like sparrow, penguin, or ostrich, we design them based on behavior abstractions. We focus on what the system needs to do rather than who specifically does it. We say, I need flying behavior, I need swimming behavior, or I need walking behavior. High-level modules depend on these behavior abstractions, and different objects simply implement them as needed. This mindset keeps your system stable even when implementations change. So what does dependency inversion really mean in simple language? It means never make your important business logic depend directly on concrete classes, libraries, or external technologies. Instead, introduce an abstraction layer using interfaces or abstract classes. Make your business logic depend on them. Let concrete implementations plug into it. When we do that, we separate what the system wants to do from how it is actually done. And that makes our applications incredibly flexible and powerful. This principle is not just theoretical. It is deeply used in real-world frameworks and enterprise systems. Modern frameworks like ASP.NET Core, Spring Boot, Angular, Nest.js, and many microservices architectures heavily rely on dependency inversion. Clean architecture, onion architecture, and hexagonal architecture are all strongly based on this principle. The reason is simple: dependency. Inversion keeps your core system safe, while letting implementation details change whenever necessary. Another massive benefit of dependency inversion is testing. When your code depends directly on real implementations, unit testing becomes extremely difficult. You may need real databases, real APIs, and real services just to test simple logic. But when your system depends on abstractions, you can simply inject mock implementations during testing. This makes unit testing faster, safer, and more reliable. So, in conclusion, dependency inversion principle is not just about writing code. It is about writing professional, future-proof software. It helps you build applications that are loosely coupled, easy to maintain, highly scalable, and extremely testable. It ensures that your high-level business logic remains protected while low-level implementations can easily evolve with time. So always remember, don't lock your system to a single implementation. Design for abstraction. Let your business logic depend on stable interfaces. Let implementations change freely without disturbing the core system. That is the real strength of the dependency inversion principle. In banking, finance, and government systems, business policies and tax rules change very frequently. New tax slabs get introduced, GST rules are modified, income tax policies change every year, interest calculation policies evolve, and regulatory rules keep getting updated. If our software is directly dependent on concrete tax calculation classes or specific rule implementations, every small regulation update forces us to modify core business logic again and again. This not only increases development effort, but also increases the risk of bugs, breaking functionality, and compliance issues. This is exactly where the dependency inversion principle becomes incredibly important. The dependency inversion principle says that high-level modules, which contain important business logic, should not directly depend on low-level modules, which perform specific tasks. Instead, both should depend on abstractions. It also states that abstractions should not depend on details, but details should depend on abstractions. In simple terms, your core banking or government application logic should not directly depend on a particular tax calculation class, interest formula, or policy engine. Instead, it should depend on an abstraction, such as an interface or abstract class, that represents the behavior, not the implementation. Let's imagine a banking system that calculates tax on financial transactions like deposits, withdrawals, international transfers, and corporate transactions. In a poorly designed system, the main transaction processing module directly depends on specific tax calculator classes like GST, Calculator 2023, VAT Calculator, or Corporate Tax Calculator. This may initially look simple, but the problem begins when regulations change. For example, next financial year, government introduces a new GST structure, modifies VAT rules, or changes corporate tax calculations. In such a case, developers must again modify the transaction processing logic. This is risky because the business logic is critical and highly sensitive. One wrong change can lead to financial loss, legal penalties, or audit failures. This is a clear violation of the dependency inversion principle, because the high-level business module is tightly coupled with low-level tax rule implementations. The system becomes rigid, fragile, and extremely difficult to maintain. Now let's see how dependency inversion solves this beautifully. Instead of directly binding business logic to concrete tax rule classes, we introduce an abstraction such as ITAXCALCULATOR or ITAXPOLICY. This abstraction simply defines the contract, how tax should be calculated, without specifying how exactly it is implemented. Now, different tax rule implementations can be plugged into this abstraction. For example, GST calculator implements iTax calculator, VAT calculator implements iTax calculator, and corporate tax calculator implements iTax calculator. The business logic does not know which tax rule class is being used. It only depends on iTax calculator. Now imagine a real-world scenario. Government updates GST rules next year. Instead of touching transaction processing logic, we simply create a new implementation like GST Calculator 2025 that also implements iTax Calculator. We replace the old module with the new one, and the business logic stays untouched. No risk, no heavy rewriting, no chance of disturbing critical systems. This makes the application future-proof, stable, compliant, and easy to maintain. Another powerful real-world scenario is government policy systems. Government portals, such as income tax systems, subsidy distribution platforms, pension systems, and social welfare systems, constantly deal with changing rules. Age eligibility rules change, benefit percentages change, new schemes are introduced, and existing ones expire. If the main system is directly tied to concrete policy logic, every policy update requires rewriting the business system. This increases cost, risk, and implementation delays. But with dependency inversion, we build a policy abstraction like iPolicy Rule or iBenefits Calculator. The system depends only on this abstraction. Different policies like old pension policy, new pension policy, subsidy policy, 2024, income tax policy, 2025, all implement that abstraction. When government introduces a new rule, we simply plug in a new policy implementation instead of rewriting business applications. The system remains stable and adaptable. Finance systems benefit massively from dependency inversion, especially in areas like loan interest calculation, EMI schedules, credit scoring logic, fraud detection rules, and compliance validation. Interest calculation formulas change, EMI regulations change. Banking compliance rules are updated based on RBI or central bank policies. If core loan processing or transaction systems are tied directly to specific rule classes, every update forces deep risky code changes. Instead, we define abstractions like I-interest calculator, I-compliance rule, I-credit score evaluator, etc. Business modules depend only on these abstractions. Implementations such as RBI Interest Rule 2024, Central Bank Rule 2025, or New Credit Policy Calculator can evolve independently without disturbing business layers. This makes enterprise finance applications extremely robust and regulatory friendly. Another major benefit of dependency inversion in government and finance systems is testing and auditing. These systems require strict testing, legal validation, security approval, and audit compliance. When your code depends directly on real implementations, testing becomes complicated because rules are hard-coded into business layers. But when everything is abstracted, auditors and testers can easily validate separate implementations of rules without affecting business systems. Mock implementations can be used for simulation and verification. This builds trust and ensures accuracy. Dependency inversion also supports scalable architecture. Many government and banking systems operate for decades. Rules change continuously, but systems survive only when they are architected for change. DIP ensures longevity. Instead of rewriting the entire application every time policies are updated, we simply update implementations. This protects investment, reduces cost, and increases system reliability. So in simple words, the dependency inversion principle in banking, finance, and government systems protects your business logic from changing policies. It allows systems to adapt without breaking. It ensures compliance changes do not destroy system stability. It helps developers update rules safely, and it helps organizations respond to legal changes quickly. To summarize, do not directly tie your banking or government business logic with tax classes, interest classes, or policy rule classes. Instead, depend on abstractions like ITAXCALCULATOR, IPOLICYRULE, IINTERESTCALCULATOR, and let the actual implementation depend on those abstractions. This keeps your application flexible, maintainable, scalable, testable, and future-ready. That is the true power of the dependency inversion principle in real-world financial and government systems. The dependency inversion principle is one of the most powerful concepts in software architecture because it changes the way we design systems from rigid, tightly coupled structures into flexible, scalable, and future-ready architectures. One of the biggest advantages of this principle is that it reduces tight coupling between modules. In traditional systems, high-level business logic directly depends on low-level implementation classes, which makes code extremely rigid. Any small change in implementation forces changes in the business layer. With dependency inversion, instead of relying on concrete classes, both high-level and low-level modules depend on abstractions. This provides tremendous flexibility because implementations can change or evolve without disturbing the core system. The business layer becomes stable and protected, while implementation choices like databases, payment gateways, notification systems, or tax policies can be swapped anytime. Another major advantage is maintainability. Real-world enterprise systems live for years and constantly evolve. Requirements change, technologies get upgraded, frameworks become outdated, and business policies shift. Without DIP, systems become harder to maintain because everything is interconnected. One change breaks 10 other things. When dependency inversion is applied, code is organized around clear contracts and interfaces. If we want to replace Razorpay with Stripe, SQL with MongoDB, email with SMS, or one tax engine with another, we simply plug in a new implementation instead of modifying the core code. This significantly reduces maintenance overhead, effort, cost, and time. Dependency inversion also makes systems highly testable. When classes depend directly on concrete implementations like real databases, APIs, hardware services, or cloud resources, unit testing becomes painful. Developers require real environments, live credentials, or complex setups to run tests. But when systems depend on abstractions, mock or fake implementations can be easily injected. This allows developers to test business logic independently without external dependencies. Testing becomes faster, safer, cheaper, and more reliable. This is one of the biggest reasons enterprise architectures and frameworks like ASP.NET Core, Spring Boot, Angular, and Microservices heavily rely on DIP. Another strong advantage is scalability. When systems are built around abstractions rather than fixed implementations, it becomes easier to extend functionality. New modules, policies, providers, or services can be added without disturbing existing working functionality. Teams can also work in parallel more effectively. One team can work on business rules while another works on implementation, because both only depend on the abstraction contract. This leads to cleaner separation of responsibilities and supports modular, layered, and hexagonal architectures. Over time, such systems can adapt to business expansion, new technology adoption, and integration with external platforms far more smoothly than tightly coupled systems. Dependency inversion also supports better long-term design thinking. It encourages developers to think in terms of what needs to be done instead of how it will be done. This results in clearer architecture, more reusable components, consistent design standards, and a strong foundation for professional software engineering. Code readability improves because interfaces explain intent better than concrete class dependencies. Systems become more logical, predictable, and professionally structured. However, like any powerful principle, dependency inversion is not free from disadvantages. One major drawback is increased complexity, especially for beginners or small teams working on simple projects. Introducing abstractions, interfaces, dependency injection containers, and layered architecture may feel unnecessary when building small applications. For example, creating interfaces and decoupling every tiny class in a two-page project may actually overcomplicate it instead of simplifying it. Beginners may also struggle to grasp the concept initially because it requires architectural thinking rather than straightforward coding. Another disadvantage is the increased number of files, interfaces, and abstraction layers. Applying DIP strictly means introducing an interface or abstraction for almost every important dependency. This leads to more code, more structure, and sometimes extra mental overhead for understanding flow. When overused, it may lead to interface pollution, where hundreds of small abstractions exist, even for trivial behavior. This can make navigation and code exploration harder if not managed properly. Performance can also be slightly affected in some cases. Because systems depend on abstractions and often use dependency injection frameworks, there is an extra layer of indirection. Calls may go through interface proxies, containers resolve dependencies, and additional runtime lookups occur. Although this performance impact is usually minimal and negligible for most business systems, it may still matter in extremely high-performance or real-time environments. When performance needs to be ultra-optimized, developers must carefully decide where DIP is necessary and where direct implementation may be acceptable. Another disadvantage is that dependency inversion requires strong discipline and architectural understanding. If developers create poor abstractions, weakly designed interfaces, or inconsistent contracts, then the system may become more confusing than helpful. Abstractions must be meaningful, stable, and well-designed. If they are rushed or randomly created, the system will end up having too many unnecessary layers, duplicated logic, and unclear responsibilities. This can lead to maintenance pain instead of improvement. There is also the risk of over-engineering. Some developers apply DIP everywhere, even where it is not needed. For small projects, prototypes, student assignments, personal tools, or limited life applications, creating abstractions and dependency structures may waste time and effort. In such scenarios, simple direct coding might be faster, cleaner, and sufficient. Dependency inversion shines most in medium to large applications, enterprise systems, long-term projects, and environments where changes are frequent. In summary, the dependency inversion principle is incredibly powerful because it reduces tight coupling, improves maintainability, enhances testability, increases scalability, and supports clean architectural design. It protects business logic from frequent changes in implementation and ensures systems remain stable, flexible, and future-ready. However, it also introduces complexity, increases code size, may slightly impact performance, requires good design discipline, and can lead to over-engineering if blindly applied. The key is balance. Use DEP wisely where it brings real architectural value, especially in enterprise systems, financial systems, government applications, large products, and evolving software platforms. When applied thoughtfully, it transforms ordinary code into professional, scalable, and robust software architecture. Because systems depend on abstractions and often use dependency injection frameworks, there is an extra layer of indirection. Calls may go through interface proxies, containers resolve dependencies, and additional runtime lookups occur. Although this performance impact is usually minimal and negligible for most business systems, it may still matter in extremely high performance or real-time environments. When performance needs to be ultra-optimized, developers must carefully decide where DIP is necessary and where direct implementation may be acceptable. Another disadvantage is that dependency inversion requires strong discipline and architectural understanding. If developers create poor abstractions, weakly designed interfaces, or inconsistent contracts, then the system may become more confusing than helpful. Abstractions must be meaningful, stable, and well-designed. If they are rushed or randomly created, the system will end up having too many unnecessary layers, duplicated logic, and unclear responsibilities. This can lead to maintenance pain instead of improvement. There is also the risk of over-engineering. Some developers apply DIP everywhere, even where it is not needed. For small projects, prototypes, student assignments, personal tools, or limited life applications, creating abstractions and dependency structures may waste time and effort. In such scenarios, simple direct coding might be faster, cleaner, and sufficient. Dependency inversion shines most in medium to large applications, enterprise systems, long-term projects, and environments where changes are frequent. In summary, the dependency inversion principle is incredibly powerful because it reduces tight coupling, improves maintainability, enhances testability, increases scalability, and supports clean architectural design. It protects business logic from frequent changes in implementation and ensures systems remain stable, flexible, and future-ready. However, it also introduces complexity, increases code size, may slightly impact performance, requires good design discipline, and can lead to over-engineering if blindly applied. The key is balance. Use DIP wisely where it brings real architectural value, especially in enterprise systems, financial systems, government applications, large products, and evolving software platforms. When applied thoughtfully, it transforms ordinary code into professional, scalable, and robust software architecture. In modern software development, microservice architecture has become one of the most popular and powerful architectural styles because it breaks large monolithic systems into smaller, independent, deployable services. Each microservice handles a dedicated business capability, such as authentication, payments, notifications, orders, users, or reporting. But even though microservices are independent units, they still need to communicate, share data, interact with external services, and follow business workflows. If microservices directly depend on each other's concrete implementations, technologies, or communication models, they become tightly coupled. This leads to fragile systems where changing one microservice breaks others, deployments become risky, upgrades become painful, and the entire purpose of microservice independence is lost. This is exactly where the dependency inversion principle plays a critical role in designing professional and stable microservice architectures. In a poorly designed microservice environment, one service directly depends on another service's exact endpoint, technology, protocol, or implementation. For example, a payment microservice might directly depend on notification. Microservices REST API structure or order service might tightly depend on inventory services database structure. Over time, if notification service changes its API contract, payment service breaks. If inventory service changes its underlying technology, order service fails. Such systems are microservices only in structure, but behave like a distributed monolith because they are tightly tied together. This is a classic violation of the dependency inversion principle in the microservices world, because high-level business services are directly depending on the low-level service implementations. Now imagine applying dependency inversion principle correctly in this scenario. DIP says that high-level modules should not depend on low-level modules. Both should depend on abstractions. In microservices, this means services should not depend directly on other services' concrete structures, implementations, or internal behaviors. Instead, they should depend on well-defined contracts, abstractions, and communication agreements. These abstractions may come in the form of API contracts, interface definitions, protocol schemas, message formats, or domain contracts. For example, instead of payment service directly depending on how notification service internally works, it depends on an abstract notification contract, such as an API specification, event structure, or interface specification. Notification service promises to follow this abstraction, and payment service trusts only the contract, not the implementation details. Now, even if notification service completely changes its internal logic, database, programming language, framework, or infrastructure, as long as it respects the abstraction, payment service remains safe and unaffected. Dependency inversion also plays a key role in microservice communication patterns. In traditional tightly coupled systems, services synchronously call each other all the time, leading to chain dependencies, latency issues, and cascading failures. With dependency inversion mindset, instead of directly depending on synchronous calls, microservices depend on messaging abstractions such as event buses, message brokers, or contract-first APIs. For example, instead of order service directly calling inventory service and waiting for a response, it may publish an order-placed event. Inventory service listens to the event and processes stock updates. The services now depend on event contracts rather than each other. This implementation follows dependency inversion because business logic relies on abstraction, event contract, not on direct service code. Another important area where DIP strengthens microservice architecture is maintainability and technology flexibility. Each microservice can use different tech stacks such as .NET, Java, Node, .js, Python, Go, or Rust. If they were directly dependent on each other's implementation, technology migration would become impossible. But with abstraction-based dependency, services can freely evolve internally while staying stable externally. This makes upgrading frameworks, updating databases, applying security policies, or refactoring internal design much safer and easier. DIP also improves testability in microservices. Testing a system where services directly depend on each other requires deploying multiple services together just to test a single module. This kills the advantage of microservices, But when services depend on abstractions rather than implementations, testing becomes extremely easy. Developers can use mock services, simulated APIs, contract testing, and stubs to validate behavior without needing real dependent services. This results in faster CI/CD pipelines, more reliable deployments, and higher confidence. Scalability is another massive benefit of DIP and microservices. If services are tightly coupled, scaling one forces scaling others, wasting cost and resources. But if they are independent through abstraction, each microservice scales independently based on its own load. For example, notification service, receiving millions of events daily, can scale horizontally without affecting payment service or order service. This results in optimal cloud cost, improved resilience, and strong fault isolation. However, dependency inversion in microservices must be applied wisely. Over-abstraction can introduce complexity. Too many contracts, unnecessary layers, or poorly designed interfaces can increase confusion. Therefore, abstractions must represent meaningful business behavior and stable agreements rather than unnecessary technical separation. The goal is not to blindly create layers, but to create logical independence that protects business stability and evolution. DIP also encourages event-driven, contract-first, interface-first thinking in microservices rather than service-to-service dependency thinking. It helps architects think from a business perspective, what behavior needs to happen, instead of which service should I call directly. This mindset differentiates professional microservice systems from poorly designed, distributed monoliths. When dependency inversion is applied consistently, microservices truly achieve the promised benefits: independent deployment, independent scalability, resilience, maintainability, and technological freedom. In simple words, the dependency inversion principle in microservice architecture ensures that microservices depend on stable abstractions, not fragile implementations. It protects the ecosystem from breaking when things change, enables continuous evolution, supports performance and scalability, and delivers truly decoupled, future-ready system design. It makes microservices stronger, smarter, and far more professional. The dependency inversion principle may sound like a programming guideline, but in reality, it is a powerful architectural philosophy. Whether you are building enterprise systems, financial platforms, government applications, or microservices, DIP teaches you to protect your core business logic from change. Technology, tools, services, and implementations will always evolve, but your business foundation should remain stable. When you build systems that depend on abstractions instead of concrete implementations, you gain flexibility, confidence, and long-term sustainability. DIP empowers teams to innovate without fear, upgrade without breaking, scale without limits, and maintain systems for years with clarity and control. In the world of microservices and modern architecture, dependency inversion is not just a good practice. It is a survival principle for building truly resilient and future-proof software. If you found this video helpful, make sure to like the video, subscribe to the channel, and share it with your developer friends. Drop your thoughts, doubts, or the next topic you want in the comments. I'd love to help you learn more. Thank you so much for watching. This is Videsh Katara channel, helping you become a smarter and stronger developer. See you in the next video. Until then, keep learning and keep coding.